Good day, everyone. I hope everybody's been having a good time in our Hack the Box University CTF for 2022. Uh, in this talk, we'll be talking about how to get into binary exploitation. And um, when we talk about binary exploitation, we have to first understand what it is and where we can use it. Taking a look at our recent Hack the Box certificates, CPTS and CBBH, we rarely covered binary exploitation. And this is because we think when we are talking about basic penetration testing and web application penetration testing, you are unlikely to need to do binary exploitation due to the nature of those tests, of those pen tests. But once you get into more advanced pen testing or senior pen testing or especially red teaming, then binary exploitation becomes unavoidable, and it becomes quite an important asset for a pen tester, especially once they get a little bit more advanced. Those who want to develop exploits and identify vulnerabilities for operating systems, for binaries and programs, then binary exploitation is a must. So what is binary exploitation? If we go into the buffer overflows on Windows module on HackTheBox Academy, it gives us a very brief introduction about binary exploitation. And it says, our primary goal with binary exploitation is to subvert the binary's execution of its, instructions in memory, subvert them in a way that benefits us as attackers. So we have user input. We want to use that input, whatever it is, to subvert the way the binary is intended to execute its instructions in a way that benefits us. For example, to get extra input into the binary, or maybe even get remote code execution or a reverse shell. There are many examples of binary exploitation. Probably the most common one is buffer overflows, but we also have things like format strings, and we have things like heap exploitation, which is the most common thing we find in modern binary attacks on operating systems and even advanced binaries. And if we want to get into some historical examples of buffer overflows or binary exploitation in general, this module also gives us some fun snippets about some historical examples of buffer overflows. For example, in 2010, iPhones running iOS 4 were jailbroken using the Green Poison jailbreak, if you remember that, if you were around that time. And that used a buffer overflow found on iOS. Of course, later on, iOS introduced some memory protections, which made it much more difficult to attack such an overflow. But back then, it was possible, and it would also give you code execution on the kernel itself, which is the highest level you can get. Another example was a stack-based buffer overflow exploit on the original PlayStation Portable, the PSP running firmware 2.0. And this vulnerability allowed us to gain unrestricted access to the core kernel of the PSP and basically execute whatever code we want, which basically people use to make a jailbreak for the PSP and allow them to install unlicensed software like games and so on. And there was later on another similar vulnerability was found in how some of the games like Grand Theft Auto, Liberty City Stories was loading the load files, and this also led to a buffer overflow, which was also utilized to gain unrestricted remote code execution. We have so many examples just for stack-based buffer overflows for this module. Obviously, we can go through them, like the one, the Twilight hack that was found in the Legend of Zelda, which also gave unrestricted kernel level access on the Nintendo Wii. And we also give a few other examples. Very recently, just a couple of years ago, a stack-based buffer overflow vulnerability was found on the PlayStation 2. When people now these days they have the ability to review the code and view the source code of the PlayStation 2 DVD player, and they actually identified a vulnerability, which was the fun fact, the very first software-based unrestricted code access on the code execution on the PlayStation 2. All of the vulnerabilities that were found back in the day for PlayStation 2 were actually hardware-based. You have to input like a memory stick and something, or do some hardware exploitation. So this gives us an overview of what binary exploitation and basically buffer overflows, how they can look like and how they can be utilized. Most of these examples are obviously quite old, because buffer overflows is no longer a very common vulnerability that you would find, because there are many protections against it. But learning it is very useful to learn binary exploitation. And this module actually even shows us some examples of how we can pop stuff into the stack or push them, and even how if we insert a very long string, how it would overflow the stack and overwrite stuff in the stack and write the ABP AIP. But what is a stack? What is ASP? What is AIP? And what is overwriting the stack and overflowing it? That's why we always recommend that when we want to get into binary exploitation, we do not directly hop into buffer overflows, even though we may be able to watch a video and understand how it's working, and maybe even write an exploit to do this buffer overflow. But once we start getting into a little bit more advanced stuff, we pass the buffer overflows. We want to get into more advanced buffer overflows, for example, with some protections, or we want to do rob chains, or we want to do advanced heap exploitation or OS exploitation. Then we would not be able to understand all of that just by understanding each topic on its own. We have to start all of that by having a solid foundation and understanding of the computer architecture and the assembly language that wraps it all. Which is why you see in our introduction to binary exploitation skill path on HackTheBox Academy, we recommend going into the assembly language module first. And this is what we will be covering next in this talk. So let's hop on to the intro to assembly language module and see what we can learn. So what is assembly language? Assembly language is the lowest level language that we humans can write to interact with the processors. We basically write a program to directly interact with the processor level instructions, which can be a very tedious task, obviously, but since it is the lowest possible, it gives us the greatest access to the processor and the greatest ability to be able to interact with the processor. If we want to see how higher level languages translate into the assembly language and lower level languages, we can see this example that's shown in the intro to assembly module. If we start with something like print hello world in Python, it would basically just print a hello world string. But what does this actually do when it comes to the processor and the memory? Python uses compiled C libraries, which basically would end up doing a write instruction in C, write one, which is the output, and then the string that we want, hello world, and then the length of the string, and then it would just exit gracefully from the program. We give the reference right about here on where you can find this in the Python open source, where this write and exit you would find how it would be linked to print. But basically, this is what it does. It uses the write syscall on C level language. And once C is compiled, for Python, it's obviously precompiled, it would actually be using these assembly instructions. This bit is for the write, and this bit down here is the syscall for exit. So basically, it is doing these assembly instructions to write something to the screen, and then these assembly instructions to exit the program. And this is the lowest level we can interact with the processor. We are telling the processor to execute the move instruction, and it puts 1 into RAX. And if this is, obviously the processor does not understand the English language, does not understand what move is, it gets actually translated into hex and binary. So 48 would, the processor would understand it as move. And then C7, C0 would understand it as RX, and then 1, it would understand it as 1, obviously, and it would say, it would understand to move 1 into RAX using the move instruction. And this, obviously, the processor at its core does not, in the silicon, does not understand hex. It understands binary, only ones and zeros as electric signals. So we would give it 48 as binary, and then C7, C0 and binary, and then 1. And it would actually be able to translate all of that and execute the move instruction. Now, by the end of the module, obviously, this will be very easy to understand. This is like quite basic syscall, but this gives us an idea of how the processor understands this print world instruction or call in Python line of code, and how it actually gets into executing it. Now, if we keep going into this section, we see once again the section mentions the value of learning assembly and learning the computer architecture for us as pen testers. And just to reiterate, having the ability to understand assembly code gives us a great advantage in being able to disassemble debug, and follow the binary instruction execution in memory and see how it goes, and which would allow us to basically reverse engineer some binaries and even identify some vulnerabilities. And even if we had access to the open source of the program that we want to debug, and we find a vulnerability in the source code itself, to be able to develop an exploit for that, we still need to learn and understand how the instructions are happening in memory, so that we can interfere with the memory execution of instructions and properly input our malicious input right into and inject it right into memory. So going into the next section, we see that this section covers computer architecture. The very first paragraph here is a very brief summary of a book called The Innovators by Walter Isaacson, which is the author best known for his autobiography of Steve Jobs. And this is a very fun read. I really recommend reading it if you want to understand and learn how computers got to where they are today, from the very basics and early day of computers in the 1850s. But what we want to know and understand is the von Neumann architecture, which is the architecture most of modern computers today, or perhaps all of them, are based on. And this architecture was developed to enable the general purpose computer principle that was proposed and later on even achieved by Alan Turing himself. And using the von Neumann architecture and Alan Turing's proposal was all built on the works of Charles Babbage in the 1850s, like I mentioned. And Charles Babbage actually proposed the concept of being able to create machines that automatically calculate some calculations, so we don't have to do them on our own. So it would automatically, without any human interference, take an algorithm that we can program, and it would actually execute it and yield the result. And Charles Babbage did not actually get into applying this proposal, but his student, Ada Lovelace, actually was the very first programmer identified today. She was able to write an algorithm using Charles Babbage's proposal and get it to actually execute automatically and yield the result. So our main takeaway of this is the von Neumann architecture, which runs most of modern computers today. So in a very simplistic view of the von Neumann architecture, we have a central processing unit, and on one side we have a short-term memory, like cache or the RAM, and on the other side we have the I/O, like the keyboard, display, or even the long-term storage. The CPU itself has the CU, which is the control unit, and the ALU, which is the arithmetic logic unit, and finally it has some registers. We will get into all of that in a bit. But this is basically the von Neumann architecture, which, as you can tell, runs most of modern computers. We know about RAM and cache and CPUs, and we know about long-term storage like SSD and HDD and displays and keyboard, which is basically the modern computer architecture. The section afterwards gets into more details about the memory, the I/O, and all of their components. We will not have time to get into details, but let's take a look at them. We first of all have the memory, which, as we discussed, have two examples, which are the cache and the random access memory. The cache, being the closest to the CPU, it is the smallest. So we have the level 1 cache, the fastest kind of caches, but it is only in kilobytes in size because it lies on each CPU core. So if we have 8 cores, we have 8 level 1 caches. Then we have the level 2 cache, which is shared by all cores, but it lies right within the CPU itself, and it makes it the second fastest after the caches. And obviously, we have something that is faster than the caches, which is the registers, but they are very small in size, just bytes. And level 2 caches are in megabytes. Also, some processors may also have the level 3 caches, and they are also in megabytes, a little bit slower than level 2 caches. Next, we have the RAM, and the RAM is much larger in size than the caches, and for that, it cannot lie directly on the CPU itself. The RAM can be in gigabytes in size or even terabytes in size to be able to handle all of the live data about any running application. And if we have things like games or data processing AI applications, they can have very large data assets, which can be stored in the RAM. And the central processing unit can be able to very quickly interact with the RAM to be able to pull those data and process them and then store them back, which is why it needs to be very fast, but it cannot lie within the CPU itself because it needs to be very large. This is why it is much larger, but also it is much slower than the cache memory. We have 4 main segments split into the RAM: the stack, the heap, the data, and the text. Each of those has its own use, and the the section goes into details of what each of those are used for and how it works. The heap flows upwards and the stack downwards, as we can see. Then we have the I/O storage. And the main thing we want to understand about those is that they connect to the CPU through what is known as bus interfaces, which are those tiny lines we can see in any motherboard. When we take a look at the green or blue motherboard, we see tiny lines running from the CPU to any external ports like the HDMI or even the RAM or any other ports. And those actually allow data to flow between the CPU, the RAM, and those I/O devices, which allows us to be able to send data from the CPU to the display or even store them in the long-term storage. Those vary in size and they can be in multiples of 4 bits. And this size basically allows us to, the bigger it is, the larger amounts of data we can send and the faster it can get. So this gives us a quick look into modern computers architecture based on the von Neumann architecture as we discussed earlier. So to wrap it all up, the closer we get to the CPU, the faster units we have. So the fastest are the registers, which are only bytes in size. Then we have the level 1 caches, which are the fastest apart from the registers, and they are kilobytes in size. Then we have level 2 and level 3 caches, which are megabytes in size, and they are also very fast. Then we have RAMs, which are gigabytes and terabytes in size, which are fast, but still much slower than the caches. And the slowest we have is the long-term storage, even though the modern M2 SSD drives are much faster than the old HDD drives, which were rotating to access data, but they are still much slower than the RAM and the caches. Now that we have a basic understanding of computer architecture, let's take a look at the CPU architecture and how it works. We mentioned earlier that we have this control unit, the CU, and the arithmetic logic unit, the ALU. So we often hear terms like this CPU has a speed of 3.0 gigahertz, and that means that this CPU can run 3 billion clock cycles every second, 3 billion hertz. And what that means is that each core in the CPU, so if we have an 8-core CPU, it can run 8 times 3 billion clock cycles every second, 24 billion clock cycles every second. But what does a clock cycle mean? We can think about it as a tick-tock happening within the CPU. So we have tick-tock, tick-tock, and each one of those can run one thing at most by the CPU. And running instructions, assembly instructions by the CPU happens in what's known as the instruction cycle, which happens in a fetch, decode, execute, and store cycle. So we start by fetching the address of the next instruction to be executed by the CPU. So what do we want to execute next? Once the processor gets to that address, it decodes what is stored there and understands what the user wants us to do. And then it actually executes this instruction. And finally, it stores the result wherever the assembly instruction instructed it to do. If we take a look at this diagram, it shows us how can this happen within the clock cycle. For example, it may take 2 clock cycles to fetch the address of the next instruction, depending on where it's stored. Maybe it's in RAM. It will take a little bit longer than if it was in cache or in a register. And then it may only take like a single cycle to decode it. And then it may take like 2 to 3 cycles to execute this instruction or even more. Now, modern processors do not do that in a sequential manner, but actually they do it in a parallel manner. Maybe it fetches the first instruction, and then as it's decoding the first instruction, it fetches the second instruction, and so on and so forth. Now, this may create some dependency issues, which is solved by what is known as the branching prediction algorithm, which is quite complicated, but basically it prevents the cycle from being in a cyclical manner where it is trying to decode something but it has not been fetched yet. It is a little bit complicated and out of the scope of this talk and the module, but that gives us a basic idea of how instructions are executed in parallel, and this gives us a basic idea of how the CPU architecture works. Finally, let's wrap this talk up by understanding the assembly language of each processor, which is known as the instruction set architecture. Each processor understands a different ISA, an instruction set architecture, and this basically is the assembly language it understands in binary. The ISA specifies the syntax and semantics of the assembly language this processor understands, and it specifies the type of instructions it can handle, the types of registers it utilizes, what kind of memory addresses it uses, and the data types it can understand, like the byte, word, double word, and so on. And the module in the section goes into more details about that. But the main thing we want to understand is that today we have two common ISAs, the CISC architecture and the RISC architecture. The CISC architecture, or Complex Instruction Set Computer, is most commonly known for Intel and AMD processors today, and the RISC architecture, the Reduced Instruction Set Computer, is most commonly known for ARM and more recently the Apple M1 processors. The CISC architecture prefers complex instructions, which means it prefers to store complex instructions right within the silicon itself, so they can be executed by a single assembly line or a single instruction cycle. And this allows the processor itself to write down to the silicon very complex instructions. And when we want to use any of them, if they are very often frequently used, we can just use a single assembly instruction. Where on the other hand, the RISC architecture preferred only storing the most commonly used instructions, hence the reduced instruction set, on the silicon itself. So only the mandatory ones are stored, and then we try to use those, the add and multiply and so on, to create more complex instructions using assembly language or using the software basically. And this allows RISC processors to execute any instruction using only one clock cycle, whereas the CISC processors will use usually more than one. And at the same time, the RISC processors would have a reduced instruction set of only about 200 supported instructions, whereas the CISC processors would have a huge variety of instructions that we can use in our disposal. So if we take a look at comparing the CISC and RISC architecture at a clock cycle level, as we saw earlier, the CISC architecture may fetch something in 2 clock cycles and then it decodes it, and at the same time it would start fetching the other, and some of those instructions may take 2 to 3 cycles. But when it comes to RISC, this can be very streamlined. Each one of them would take 1 clock cycle exactly, which allows it to easily predict what's going to happen next and when it's going to happen. Now, in the past, having complex instructions written directly in the silicon allowed us to execute those complex instructions very fast because they were written directly in the silicon in a very efficient manner. Whereas if we want to write something in software, it would be less efficient because we humans are not very efficient in writing code. But today, with having very advanced abilities of writing code and very advanced AI written assembly code, we can have very efficient assembly code that runs very efficient software, which is starting to make RISC processors become much more efficient than CISC processors. And at the same time, because it is only taking 1 clock cycle per instruction, it is also much more energy efficient, which is why we are seeing modern MacBooks using much less energy than their Intel counterparts. And at the same time, the iPhones or mobile phones that we use much less energy to execute applications when compared to modern laptops and computers. So this gives us a brief look into what the main differences between RISC and CISC are, and what an ISA or the assembly language of each processor is, and how it can make the difference between what we see as ARM or M1 processors versus the Intel and AMD processors, and how that ISA or assembly language can make a difference. And with that, we can wrap up today's talk by hopefully having understood the CPU architecture and the different ISAs between each CPUs, and the general computer architecture and the assembly language underlying each of them. Now, you can go through the module and read each of those sections to get a general idea of what assembly language and computer architecture is, and then you can go through the entire module, which is quite lengthy and full of details, to understand the x86 64 assembly language and how you can write assembly instructions and assembly language and understand the x86 assembly language and architecture. And once you understand one assembly language, it becomes much easier to understand other assembly languages, especially if you understand how assembly language works when it comes to processors and how the computer architecture works in general. And hopefully, once you complete the Intro to Assembly module in HackTheBox Academy, you would get a very solid foundation of how assembly language runs and how programs use the modern computer architecture and the assembly language to execute their instructions. And this hopefully would sit you on a very solid foundation for binary exploitation greatness. Thank you everyone for taking the time to attend this talk, and I hope it was entertaining and you had a thing or two to learn from this talk. Thanks everyone, and see you next time.